This session is about parameterized complexity and parameterized algorithms. So in the coming 3 lectures, I will introduce this area of parameterized complexity, and we'll discuss a few techniques that's used in parameterized algorithm design. Okay. So the first question is, what are parameterized algorithms? So just curious, how many of you have heard about parameterized algorithms before, or know what are parameterized algorithms? Show of hands. Very few. Okay, good. Okay. So let's start with the motivation for parameterized algorithms. So it's the most well used, or most, in some sense, sometimes dreaded word in the world of algorithm design, NP completeness. Okay. So this is the motivation. So I'm sure all of you know what NP completeness mean, or what does it mean to say that a problem phi is NP complete. Okay. Of course, there are definitions of what is class NP and so on. But what is the implication? What is the immediate implication of saying that the problem is NP complete? Yes. What can you say about, or what is widely believed about NP complete problem? That it is hard to solve. That's in polynomial. So something like this. Of course, we are assuming anyway. We don't know it for sure, but it's widely believed that. So unless P equal to NP, there cannot be an algorithm that solves the general instance of pi. I mean all instances of pi exactly and the running time is polynomial. So this is not possible. So let's look at the keywords in this implication. There cannot be an algorithm that solves the general instance. It's important that by general instance mean the most general instance. In other words, any instance of pi. Exactly. What do I mean by exactly solving a problem? Find the exact solution. For example, if you are looking for the minimum vertex cover problem, what is the minimum value possible for that? You want to get that value. That's what I mean by exactly solving the problem. And also the running time of the algorithm cannot be polynomial in input size. So all these keywords are there, and it is possible, or it may be possible that if you ignore one of these keywords for the problem, it may actually have efficient algorithms. For example, look at this, the general instance. So as an example, you know that vertex cover is NP complete in graphs. Okay, so you might have already proved it in your class. Okay, so you know that vertex cover problem is NP complete in general graphs. But when you take some special instances of the graph, for example, graphs like trees, bipartite graphs, etc., vertex cover is polynomial time solvable. There exists a polynomial time algorithm for solving vertex cover in trees and bipartite graphs and many other graphs. So when you ignore this general instance part there, you are getting a good algorithm or an efficient algorithm. In this case, a polynomial time algorithm. Similarly, if you ignore this exactly part, so in some cases it is possible that you are not looking for an exact solution, you are looking for a solution which is near to, which is not very far from the exact solution. It may be possible. I'm sure today you have seen in the first session, right? So vertex cover again, it's NP complete, but there exists an approximate, you can get two approximation in polynomial time very easily. I'm sure Professor Murli has already discussed it, right? So if you ignore this exactly part also, at least for some problems you can get efficient algorithms. Okay, right. And the third keyword, polynomial, it's trivial to see, right? I ignore the polynomial part altogether. I can always get a exponential algorithm to solve the problem. Brute force, like even if you just take brute force, it takes in exponential time, it solves most of the problems. Okay. So all these keywords, once one or more of them are ignored, there are problems. I'm not claiming for all problems, but there are problems which may be efficiently solved. Okay. So in parameterized algorithms, what we are going to do is, we are kind of partially ignoring two of these keywords. Okay. So we'll ignore general instance, but again, it's not like saying, okay, it is you are taking trees or something. Right? So you are taking a special class of instance, okay, and for looking at the problem for that class of instance, and proving that for that class of instance you get efficient algorithm. Also, you are partially ignoring polynomial. So, but then are you getting an exponential algorithm? Then I just mentioned that it is trivial, right? Like in most cases, it's trivial. So it is not exponential, like in the sense that it is not exponential in the input size. Okay, that's what we are trying to avoid. Okay. So I'll explain more. So here, the problem instance. Okay. So in the world of parameterized complexity, usually what you have a problem instance for solving the problem, and you usually call the size of it is n or n plus m or whatever, right? So you have a problem instance. In addition to the actual problem instance, you have one more thing which we call as the parameter. I'll explain what do you mean by parameter. Okay. So you have a parameter also, okay, and okay. So the value of the parameter is assumed to be much smaller than the input size. Okay, so you assume, or it is believed, or okay, it's assumed that for your input instances, the value of the parameter is small. Okay, and what are you looking for? You're looking for an algorithm which exactly solves this problem instance. Okay, but this running time, it is exponential only in the parameter, but polynomial in the input size. So we get a running time. We get an exact algorithm that solves the problem with in time, polynomial in the input size, but exponential in the parameter. And why can I say that this is efficient? Because my assumption is that parameter is small, right? So it's much smaller than the input size. Okay, so the running time is polynomial in input size. It is exponential in the parameter, but I'm okay with that because I've assumed that the parameter is less. Okay. Okay, so this is the idea. So for every problem, you add a parameter to it. Parameter can be anything, like can be a structural parameter of the input, or okay, we'll see what can be the parameters. Okay, so going to a formal definition. So this. So usually when you are solving a problem, you have an alphabet sigma, and you check whether the problem instance x is in sigma or not, right? But here the problem instance contains a sigma and alphabet, also a positive integer, small positive integer. Okay, so parameterized problem, it's a language. L is subset of an alphabet, and it's an ordered pair of alphabet and positive number. And okay, so and for this x comma k, the second element here, it's called the parameter of the problem. And what are you trying to design here? You are designing an algorithm, okay, which is called a fixed parameter tractable algorithm or an FPT algorithm. If it solves the problem exactly. And what is the running time for this? F of k, k is the parameter, f is just a computable function. It can be exponential also. Most of the cases it is exponential. And what is the function on the input size x? It is polynomial. Size of input is polynomial in something. Okay, so this is the definition. Okay, so again I repeat. Here we have an input and a parameter. So we say that this is the problem parameterized by the given parameter k, and then algorithm for a parameterized problem is an FPT algorithm if it solves the problem exactly and in running time this much. An exponential, there can be an exponential factor to it, but the exponential explosion is limited to only the parameter, whereas in the input size it is polynomial. So what happens here when k is very small? Let's say k is like a constant, a small constant value, f of k, even if you take 2 to the power 2 to the power 2 to the power k, a big exponential function, when k is small, that value is small, right? It's as good as a constant. And what do you have? Remaining, what do you have? A polynomial time, running time. Okay, so this becomes efficient when k is small. So this is what you're looking for. And again, the motivation for this problem is a lot of problems, a lot of real-world applications of problem. Like for example, you take a graph problem. A number of parameters are small in real-world applications. You can find applications where some parameter is small. So it makes sense to use an FPT algorithm in such a case. Okay. So is the definition clear to all of you? And the value of a parameter. Yeah, you only give a instance, right? A word. F is some function in k, can be exponential also. Used to bound. So this is the running time. So the running time is bounded by this f of k. You can even call this n. F of k polynomial n. Okay, so f of k can be some exponential function. Okay. Okay. Any other questions? Yes.
Parameters small means how small, right?
We are not going to define that. Right. So we have a function. Right. The running time is maybe exponential in k. Oh, it's a positive integer, right? It's not going less than 1. It won't go less than 1. Okay. So the idea here is you take the rate in which this running time grows, this function grows. It will be very less compared to some. So, like, even if algorithms with running time n to the power k, it is not an FPT. It's not considered an FPT running time. Okay? But some, like, you have k separate and polynomial in n, that is an FPT. Okay. Right. So clear? Okay. Now the question is, okay, I've said parameter. What can be a parameter for a given problem? Okay. So one standard parameter, or we'll call it a parameterized okay, let's do the standard parameter itself, is the output size, the size of the output. Okay, so let's take the vertex cover problem. And what is the minimum vertex cover problem? Find a vertex, given a graph, find a vertex cover of the minimum size. An equivalent way of asking this is, given a graph, is there a vertex cover of size k? Right? So are you convinced that they are equivalent? Okay, so in this case, what is the size of the vertex cover? Size is the size of the output that you are looking for. It is k. So that can be a pair. So it's called standard parameterization, and it's used for many problems. Okay, so one of the standard parameter is output size. Okay, and other are structural parameters of the input. For example, if you are in a graph problem, see, parameter can be any parameter of the graph, like any property of the graph, like so max degree, when the maximum degree is small or the maximum degree is k, genus of the graph, tree width of the graph, or any other parameter, the FES of the graph, the vertex cover of the graph, you can like think of it. So the basic, I think the rule of thumb is that there should be some application where this parameter is small for the graph or input. Okay. Now, satisfiability problems, you have all of you have seen stat problems, right? So, given n variables and n clauses, you have to find an assignment with certain properties. Okay. So, for this kind of problems, what can be number of clauses, number of variables can be number of variables can be a parameter, number of clauses that needs to be satisfied, and so on. And another example, geometric problems, dimension of the space you are working in, and or the number of points with certain properties, or number of objects with certain property, or some other geometric property of the input. All this can be. Okay. Right. And also, you can think about more than one parameter, right? So what if you are working on a graph where the maximum degree and tree width both are small? Okay. So in this case, both are parameters, or in other words, combination of max degree and tree width is a parameter. But parameter, I said it should be a positive integer. Therefore, you consider, like in the case where parameters are k, l, and so on, technically the parameter is k plus l plus. Okay, so in this case, you are looking for a running time f of k plus l and n to the power some constant or polynomial in n. Okay, right. So this is what we are looking for. This is the FPT running time, and the concept of parameters is clear to all of you. Okay, so the next question is this. So we have seen what parameterized, what the parameterized problem is. Does every parameterized problem admit an FPT algorithm? What will be your conjecture? See, like in other cases we have seen, right? In polynomial time we have seen there are some problems which have polynomial time running time, and there are some hard problems, right? So some problems you don't expect polynomial time running, or some problems which are considered intractable. So, is there a similar intractable problems, similar set of intractable problems in parameterized problems also? So that's, I'm asking, does every parameterized problem admit an FPT algorithm? And the answer is most likely not. Okay, so it's widely believed that there are some problems for which even an FPT algorithm does not exist. Okay, and similar to this P, NP, NP hard classes, the complexity class and the classical complexity. Here also we have some complexity classes which tells you about this, the tractability or intractability of NP hard, of parameterized problems. For example, so there is this class called FPT. FPT contains all fixed parameter tractable problems, or all parameterized problems for which an FPT algorithm is designed. Okay, and in like similar to this NP complete thing in classical complexity, we have classical complexity there is only one NP class. here there is a series of classes. There is a W1, W2, W3 onwards, or in general you can say WI, complexity class, and it contains problems which are believed to be hard or believed to be intractable. Okay, and this is okay. So this is a relation that we know, that is FPT, the one that contains all tractable problems. It's a subset of W1, which in turn is a subset of W2 and all. So for us, when we are designing algorithm, all this, there are some technical differences between W1, W2, W1 and W2, W2 and W3 and so on. But when you're designing algorithm, thing that you have to keep in mind is this: whatever WI contains problem which cannot, or I won't say cannot, which may not have FPT algorithms at all. Okay, unless of course it is built on the assumptions P equal to NP, and also this. So we have also this assumption that FPT not equal to the class FPT not equal to W1. Yes. I okay. So okay, I don't want to go into the technicalities of it, but it is it's a class of problems which can be reduced into a SAT problem with a given weft. So based on if you are reducing it into a weft 1 circuit, it is a W1. It is in W1 class. So weft 2, it is W2 and so on. Again, for the purpose of algorithm design, all are similar. Similar to? But in polynomial you don't have like two or more than one class, right? All the intractable problems are in NP. NP complete. That's it, right? Sigma 1, sigma 2, A1, A2. Okay, I don't know in which sense you say it's similar, right? Okay, you can say that it's kind of analogous to that. Okay. Here? Oh, that is W3. There are W3, W4 at once. Yeah. Okay. Right. And okay, some problems. So the problems which are in W1, W2, etc. We call it, in general, we call it W hard problems. And the problems, some of the problems which are known to be W hard are this. K-clique depend. Okay, so what is K-clique problem? Finding a clique of size K, finding a K-clique. Okay, so given a graph, decide whether there is a K-clique in the graph, and this is parameterized by K. Given K independent set, it's parameterized by K. K dominating set, checking whether there is a dominating set of size K, that problem, parameterized by K. Okay. So, okay, you have to keep in mind that the problem and a parameter both forms the instance of a parameterized problem. See, some problems, a clique problem, I think when parameterized by K is W hard, that's we know. Maybe when you parameterize by some other parameter, it might have an FPT algorithm. That's possible. Okay. Okay. So this is the definition of parameterized complexity and what you mean by an FPT running time parameterized algorithm. Okay. So now we'll see some techniques to design FPT algorithms. So there are more than what I'm going to discuss in the coming 3 lectures. We'll see only some basic techniques. The first one I want to discuss is bounded search trees. Okay. So ignore this. So So bounded search trees work like this. So for any problem, there is a solution space, right? Or there is a space where all potential solutions are there. And you know that if you do an exhaustive search in that solution space, you will get the solution. Okay, right? So here the idea is we'll also build a search space or a space containing potential solution. Okay, and we'll search the entire search space, but we'll make sure that the search space is bounded by, the size of the search space is bounded by function of the parameter. Okay, so if you are searching a space whose size is bounded by bounded by k, how much time will it take to search it? It's again a function of k, right? So that's what we are trying to use. So here this search space is usually represented by a search tree. I'll explain what a search tree is, hence the name bounded search tree. So this technique is also known as branching algorithms. Okay. So I think it will be more clear when we see an example. So let's go to in the first example in any algorithm class, the vertex cover problem. So given a graph G, V prime is a subset of vertex set. It's a vertex cover if for every edge at least one endpoint of E is in V prime. Okay, so this is the definition, and this is the parameterized problem. So we are given an undirected graph. Question is, there a vertex cover V prime of size at most k, and the parameter is k. And what are we looking for? An algorithm with running time, some f of k, polynomial in n. Okay. So here we are going to build the search tree for this. Okay. So this is a fact, right? So you take any edge in the graph. One of its endpoint should be in the vertex cover. That's the definition of vertex cover, right? Okay. Now we will branch on. When I say branch on, what I mean is we'll consider both possibilities. Okay, we'll draw a tree where one branch of the tree will consider the possibility that U is in the vertex cover, and there is another branch which will consider the possibility that B is in the vertex cover. Okay, and it's an exhaustive search because you know that either U or V should be in the vertex cover, right? Okay. So how is our okay. Okay. So let's say I have this graph. Maybe there is something else. Okay. So I start with some edge. Start with this edge. Okay, maybe I'll start with UV itself. Okay. So the root of the search tree contains nothing. It's just an empty set. And now the child node of this root node, it will one of the child node it will add U to the vertex cover, and the other child node will consider V to this. So basically what I'm doing is I'm going to add U to the solution and recursively solve the rest of the problem. Okay. So in this branch what happens? I added U, right? So I need not consider any of these edges. All these edges are covered, right? Okay. So I will take the next edge which is not covered, which can be, let's say, XV, right? Now at this stage I again branch on whether I take X or I take V. Okay. So again here I take X and here I take V. Okay. And I continue. What happens on this side? When I have, when I take V, so I take V, again this and this are covered. So I take the next, some edge which is not covered by V. Let's take X and U. So again here I will branch on. So on this branch X is taken, on this branch U is taken. Okay. So what does this node correspond to? This node correspond to a partial solution where X is in the solution and U is in the solution. Similarly here it will this node correspond to a solution where X is in the solution and V is also in the partial solution. Okay, and then we repeat. Okay, then we take the next edge which is not covered and again branch on it. Right. Okay, so and I continue till I get a vertex cover, or till I can say that there is a vertex cover or there is no vertex cover of size k. So this is the algorithm works. So is it clear? Okay. Now, what will be the running time of this algorithm? Is it FPT? That's what you are interested in, right? So at each node, what is the work done? How much work you are doing at each node? You are considering so let's say you are deleting some edges which are already covered and take the next edge which is not covered, right? All this can be done in polynomial running time. Okay, right. So the work done at each node is polynomial and the total work done will be polynomial, some polynomial multiplied by the number of nodes in the search tree. How many nodes can be there in the search tree? Essentially you are taking a subset of vertices and, right? So can it go like 2 power n, because 2 power n is the total number of subsets of size n, of a set of size n. Yes, right? So here what happens, at this level of the tree, you have taken either U or V. That means your partial vertex cover contains one vertex, right? In the next level, all these nodes correspond to a partial solution which contains 2, right? And it goes on like this. So when you reach level K, all these nodes correspond to partial solutions which have K vertices in the vertex cover. But that is our budget, right? We cannot take more than K, right? So when we reach K, when we at height K or less, if we have already reached a node where every edge is covered, we say yes. We say yes, there is a vertex cover of size K. Otherwise, there cannot be a vertex cover, because all of these, one of our possible choices. We are exhaustively searching the choices. Okay. So what will be the size of this tree, the search tree? It's a binary tree. Its degree is bounded by 2 and the height is bounded by k, 2 power k. So what is the total running time? So 2 power k multiplied by the polynomial work which is done. So that's what we need also, right? Okay, so we branch on. So we get a vertex cover, for vertex cover parameterized by k, running time of, okay, so I use this notation, this calligraphic O. This hides basically polynomial polynomial running times in n. Okay, so so I should say that in FPT running time, people have looked at both, like, whenever you have an algorithm, you try to optimize the running time. So here optimization can happen in 2 ways. Either you can optimize this exponential function, or you can even optimize the polynomial function in n, or you can do both also. But right now, for the purpose of this talk, we are interested in optimizing this. And therefore, I am using this notation, calligraphic O. This contains some polynomial in n factors also, but I'm not concerned about it. Okay, right. So We have a vertex cover parameterized by k and running time is 2 power k. Okay. So we got our FPT algorithm. So that's the first result of the day. Vertex cover parameterized by the solution size is FPT and the rest is an FPT of size of running time 2 power k. And in the next we'll try to improve this running time using another branching algorithm. Okay? Are you with me so far? Okay. So, what is the improved branching algorithm? So, previous branching algorithm, we use this fact that you take every edge, one of its endpoints will be in the vertex cover. Here we'll use another fact. You take any vertex in the graph. There are two possibilities. Either that vertex is in the vertex cover. What if it is not? All its neighbors will be in the vertex cover, right? So you take some graph, some vertex in the graph. If this, let's say you know that V is not in the vertex cover, someone has to cover all these edges, right? So we have to take the other vertex, other endpoint of the edge, and they are the neighbors of V. Okay. So for every vertex, V, either V is in the vertex cover or all the elements in the neighborhood of V is in the vertex cover. We know this. So we are going to branch on this. Okay. So we take every vertex. In one branch, we will take V. For each vertex V, on one branch, we'll add V to the vertex cover. On the other branch, we will add all its neighbors to the vertex cover. It's very similar to the previous algorithm, but the idea is, can we reduce or can we improve the running time by reducing the size of the tree, size of the search tree. Okay. So on one branch we are adding V. So our budget was k. We have already we started with k. We have added one vertex to it, and your budget becomes k minus 1. What happens on the other branch? We are adding all the neighbors. So what's happened to k now? K is decreased by, depends on the degree of V. Yes. Right? Okay. So we'll try to increase the degree of V, right? So that what happens when we are adding more. What happens when we are adding more elements? So here we have V and here we have neighborhood of V. So here budget was k. Here we becomes k minus 1. Here become k minus something. Okay. So let's say it becomes k minus something large, k minus 4, 5 or something. So this branch, the height of this branch will get reduced, right? Okay. So eventually that means the size of the tree is also reduced. Okay. So we are trying to increase this. Okay. So let's see how much can we increase the degree of V. For example, if what is bad for us? All the vertices are of small degree, right? So what happens when all the vertices are of let's say degree 1 in a graph? What does the graph look like? What does the graph look like? Yeah, it's kind of a match. Okay. Graph looks, so for this type of graph, finding the vertex cover is simple, right? You just take for every vertex, it's trivial. You don't need it's polynomial type. Okay, so we need not consider this graphs. So what if, let's go to the next step. What if every vertex is of degree 2? At least 2. Sorry, at most. It's a path or a cycle. And how do you find a vertex cover of path or a cycle? Again, polynomial time. You have seen all this, right? Okay. So these two cases can be ignored, right? So you can assume that there exists a vertex of size or of degree 3, at least 3. Okay. So now what happens if that is the case? We started with K, and in this node you are adding one vertex to the vertex cover, and this node you are adding at least 3 vertices. Okay, because you can always find a vertex of degree at least 3, right? So here you are adding at least 3 vertices. So what happens to the budget? So here it is K minus 1, here it is K minus 3. It can be smaller also, it can be at most K minus 3. And the same thing, right? In every branch you can branch it into 2 branches, such that one branch reduces the budget by 1 and the other branch reduces the budget by 3. Okay. So then what happens to the size of the tree? What can you say about the size of the tree? Right? Okay. So you have assumed that degree is at least 3, maximum degree is at least 3, and in such a case, the size of the tree is given by this recurrence. T of K is one side, it's K minus 1, and the other side, the budget is K minus 3, at most K minus 3. And this recurrence will give you, it will solve to this 1.4656 to the power K. So by similar arguments as before, we get an FPT algorithm whose running time is for some polynomial in N and 1.4656 to the power K, which is an improvement over 2 power K. No, so you are assuming that in the graph there exists a vertex, there exists at least one vertex of degree at least 3. Otherwise, if there is no such vertex, it's either these two cases, and then you stop. If you reach such a stage, then you stop. Yeah, then you trivially solve, like polynomial time you solve it. Okay. No, maximum degrees. So what I meant to say is there exists a vertex of degree at least 3. It's same maximum degrees at least 3. Okay. Questions? Okay.
For some vertex, the T of K equal to T of K minus 1 plus T of K minus 1. That would be true at all levels.
Yes. So if you reach a level where the maximum degree is not 3, then for the rest of the graph you can solve it polynomial time, right? So at that node you run the polynomial algorithm and get solution.
When we go to T of K minus 1, then we have to choose the vertex with the maximum degree.
We have to choose a vertex with degree at least 3. Need not be always maximum degree. I think maximum degree will help, practically it will help, but for analysis purposes this is enough. Okay? Right. So obviously you can ask, why did we stop at 2? Like, why did we try to find a vertex, find a graph with maximum degree at least 4? Then we would have got K minus 1 plus T K minus 4. Right? We cannot do it because vertex cover on degree bounded by 3 graphs, it's not polynomial time, it's NP hat. So by this approach, this is the best we can get. Okay. Okay. So if it is clear to you, we'll move to a different problem. Feedback vertex set. Yes. Oh, okay. So this worked because for maximum degree 1 and 2 are polynomial time solver, we could trivially solve it. But when the degree is, even for degree bounded by 3 graphs, vertex cover is not polynomial time. So we cannot use it as it is. Maybe there are, like, clever ways to do that. You cannot use it as like. Okay? Okay. So let's go to the next problem. Feedback vertex set problem. So this is the definition. Given a graph, feedback vertex set is a subset of vertices such that if you remove those vertices, the graph becomes a cyclic. Okay, so for example, so if you take this vertex, it is not enough, right? So these two vertices, if you remove these two vertices from the graph, you get only this edge and it is a cyclic. Okay, or you can even take one of these vertex. Right? If you just remove this vertex, all these edges will be deleted. What you get is a path. Again, a cyclic. Okay. So on feedback vertex set, you have to delete. So in a way, for every cycle, you have to choose at least one vertex from it. Okay, and such that when you remove those vertices, what remains is an acyclic graph. So this is feedback vertex set, and the problem is this: given an undirected graph, okay, I'm just saying undirected, need not be simple graph. Given an undirected graph, does G have a feedback vertex set of size k, of k vertices? Parameter is again k. Okay, right. So let's try to use a branching algorithm to solve this. So here, what we are doing is, first step is we'll do some pre-processing to the graph, to the input. Okay, that means by pre-processing I mean I take care of some simple cases in polynomial time such that the instance is it's equivalent to the instance that you started with. Okay, so we'll set it. So this is my first pre-processing rule. I call it a reduction rule. So my first reduction is there. If there is a vertex with a loop is like a self loop, an edge which starts at a vertex and enters the same vertex. So if I have a vertex with a loop, see, this is a cycle, right? A loop is a cycle. Okay, so if there is a loop, what can you say about the feedback vertex set? We have to take a vertex. We have to choose a vertex from every cycle. So from the loop, there is no other vertex to be chosen. You have to choose V. Okay, so then you know that V is in the vertex feedback vertex set. Okay, so this is it. If there is a loop at a vertex V, delete V from the graph and decrease k by 1. What I am essentially doing is I am adding V to my feedback vertex set. So then I delete V from the graph. Anyway, V is part of feedback vertex set, and all the cycles for which V is a part of is already taken care of. So we delete all the vertex V itself and decrease k by 1 because we have added one vertex to the feedback vertex set. So the budget reduces from k to k minus 1. Okay. So we decrease k by 1. So this is the first reduction rule. So this I do for any loop present in the graph. Okay. Once I have exhaustively done this, my second reduction rule is, if there is an edge of multiplicity larger than 2, reduce its multiplicity to 2. That means if I have multi-edges, more than 2 multi-edges between 2 vertices. So you have 2 vertices UV, you have this edge, have a number of edges between them. Okay. In this case, you just delete all the edges between U and V except for 2 of them. Okay. The multiplicity of UV is 2. Okay. Why is this okay? Is it okay? Like, can I say that the answer to, after I doing this reduction, is same as the answer to the original instance? Yes. So cycles involving UV and other edges still remain, because you still have this edge, 2 edges UV between them. So, but why 2? Why I should have deleted every edge except 1. They form a cycle, right? So they form a cycle. So this is a cycle itself that needs to be taken care of. If that is taken care of, all the other cycles like that is also taken care of, because all of them involve just U and V. Okay, so that's the second reduction rule. If there is an edge of multiplicity larger than 2, reduce its multiplicity to 2. Okay. Okay, this is easy to see. If there is a vertex of degree at most 1, delete. So if there is a vertex of degree 1, it cannot be part of any cycle, right? Okay. So that vertex is not interesting to us, so we just delete it. So this is take care of trivial cases, so that the resulting after this, whatever instance we have, it's simple, right, or less sense. Last reduction rule is this. If there is a vertex of degree 2, delete that vertex and connect it 2 neighbors by a new edge. So what I am doing is some kind of short circuit. So you have a vertex of degree exactly 2. Okay. So we have only two neighbors, let's say U and U prime. Okay. So what you do is, if for every such vertex you delete V, okay, and you delete these 2 edges. Of course, when you delete U, these 2 will go, and instead you will add this edge, U prime. Okay, so is the reduction clear to you? So we have V, which was a degree 2 vertex, and I delete every such vertex and kind of join their neighbors. Okay, so I had to I'm claiming that this is okay. The feedback vertex set, the solution of the feedback vertex set is not changing by this. Why is that true? We deleted V. Yes. Okay. So what happens if V is part of some other cycle? Can we? Is that cycle still there? No, it can be part of many cycles.
Yeah, but all of them go through U and V.
Yes, right. So V can be part of many cycles, but all these cycles will contain U and U prime. Right? Because V is of degree 2, any cycle through V, it should come by this and go to this. Okay. So any cycle that contains V will contain U as well as U prime. Okay. So if you are for that cycle, you are not deleting any cycle essentially, right? So you have you have some cycle like this. Let's say you have some cycle like this. It is like this now. So this cycle, so in the reduced instance you will hit this cycle, right? You'll take care of this cycle. So in the original instance, this is taken care of. What if u prime itself is a cycle? Yes, right. So what if so it was like this, okay? So it becomes u prime like this, okay? Right, u prime. Okay. So what you do now is you have these 4 reduction rules. You extend you use it, or you use this reduction rule till you cannot use any of them, right? So just see, for example, now when you are adding this, this multiplicity may increase, right? Earlier suppose there were 2 edges, now it becomes 3 edges. But what was your second reduction rule? That if there is multiplicity 2, you delete all the edges and make multiplicity. Then you use that reduction rule. So you exhaustively use all these reduction rules till none of them applies. Okay, right. And the point of doing all this is, so after this, we'll get a graph like this. So we have a graph which contains no loops and which contains only single and double edges, and it has minimum vertex degree of at least 3. Because degree 1 and degree 2 you have already deleted, right? Okay. And for such a graph, you have some more structure, okay? Such graphs with minimum degree 3, no self loops and all have some more structure. What is the structure I am talking about? So for such a graph, let V1, let you order the, V1, V2, Vn be an ordering of the vertices in the according to their degrees, in the descending order of their degrees. Okay, V1, V2 up to Vn is an order. So V1 is the highest degree vertex in it, and so on. Vn is the smallest degree. Okay. And V3k, it's a set of the first 3k vertices. V1, V2, V3k. Now you can prove this, that every feedback vertex set in G, the reduced instance G of size at most k, contains at least one vertex from V3k. Okay, so you order the vertices according to their degree. From the first 3k vertices, at least one of them should be in the feedback vertices. So I am not proving this lemma. You can go back and try if you can prove, otherwise we can even discuss it later. Okay, so after reduction rules, we get our graph with more structure for which this statement is true. Okay. Every feedback vertex set in G is of size at most k contains at least one vertex of V3k. Okay. Now can I do something about it? We got some more information about the solution. We know that from V1 to V1, V2 to V3k, one of them is, at least one of them is in the FES, if there exists an FES. Okay, so you want to branch basically. Do you branch off? What do you branch off? Yes. So we know that one of them is in the solution. You branch on each of them and add it to the solution and see what happens. Okay, so that's it. We know that one of them is in the solution. So on every branch, you will add one to the solution. Okay. So, and what do when you add a vertex? Then you delete that vertex from the graph, and for the remaining graph, again run all these reduction rules if it is applicable. Again use this lemma. Again branch. Okay. So after you added this, in the next branch again you will have some. So here it will be 3. So k minus 1. So it goes till 3k minus 1. Okay, that's it. Okay, so The crux of designing a branching algorithm is this, like bring or find out a statement from where you can make a choice and branch on all those choices. Okay. So what will be the running time of this algorithm? So is this step clear? Okay, we have proved that there exists one vertex in V3K in FPS. Okay, we'll guess which vertex is in the FPS, and then we recurse on it. Again, by the similar to vertex cover, we cannot branch more than K times. The height of the tree cannot be more than K, right? Because at some stage, at every level, we are taking one vertex. We are decreasing the budget by one. So we cannot go more than K. So we have a tree, and what is the time? What is the work done at each node? At each node, again, you are like deleting some vertices, deleting some edges, then reduction. All the reduction rules take polynomial time, right? So all these are polynomial. So it's just polynomial. Running time will depend on the size of the tree, and the size of the tree is, you have a tree where every node has at most 3K child nodes, and height of the tree is at most K. So, yeah, 3K to the power K. So we have an FPT algorithm that solves feedback vertex set in 3K to the power K. Okay. Okay. Right. So this is branching algorithm for feedback vertex set. Any questions? Okay. So I should say, we'll go to the next technique. So I should say that all the algorithms that we discussed in the lecture is intentionally the simple ones. So you are encouraged to go back and read more complex algorithms. Okay. Next is kernelization. Okay. So we have discussed bounded search tree algorithms or branching algorithms. The next technique for FPT algorithm design is kernelization. It's a very important topic. It's independent of FPT. Like like kernelization itself is a big topic. Okay, I'll explain. So I'll explain what kernelization is. Yeah. So we saw some pre-processing done during the FES branching algorithm. So kernelization is also like this. So you start with an instance, pre-process the instance, or reduce the instance. When I say reduce, I mean is you start with an instance, do some pre-processing such that its size become smaller, right? And again run the same pre-processing and again make it smaller. Okay, that is the idea of kernelization. Okay. Of course, you cannot go on and on doing that. Why? Because these are NP-hard problems, right? You cannot do it, you cannot keep on reducing the problem such that it becomes constant size, then it becomes polynomial time, right? So obviously you cannot do it till the instance become very small. But our idea is we'll continue this, we'll continue pre-processing till the new instance or the reduced instance formed is of size a function of k, is of size some g of k. Okay, and what is the advantage of reducing the size of the instance to g of k? Yeah. So we are starting with an instance of size n, okay, and a parameter k, and then you keep on reducing to get an instance of size some f of k. Okay, so what is the advantage in doing that? The size of the instance is bounded by a function of k. Even if you do a brute force on that instance, how much time it will take? It will still be a function of k, right? So that is the idea. So we pre-process it till the reduced instance, the size of the reduced instance is bounded by a function of the parameter. So bounded by a function of k. Then this function, this reduced instance can be like either you can use some other technique like branching algorithm on it, or you can even brute force. By brute force you solve it, still you get an FPT running time. Okay, right. Okay, so that is kernelization. So pre-process reduce the instance to get an equivalent instance. So the technical meaning of equivalent instance is this. So let's say I and I prime, they are equivalent if the following holds, like I is a yes instance if and only if I prime is a yes instance. In other words, let's say if we are dealing with vertex cover, I has a vertex cover size k if and only if I prime has a vertex cover size k prime. Okay, so I kind of hand waved a little bit there. See, what I mean to say is this. So you start with an instance I and a parameter k, okay, and you reduce this in polynomial time, let's say, to get a new instance I prime, k prime, and the parameter may also change to k prime, and they are equivalent if ik is a yes instance if and only if I prime k prime is a yes instance. For example, if there is a vertex cover problem, I has a vertex cover of size k if and only if I prime has a vertex cover of size k prime. Okay, and this is called, this I prime k prime is called the kernel of the problem. Okay, right. So more technical term is this. Kernelization algorithm or a kernel is an algorithm that given an instance of a parameterized problem reduces into an equivalent instance x prime k prime such that the size of the reduced instance is a function of k, some g of k where g is a computable function. And depending on what the value of g, we can say, or the value of g is known as the size of the kernel. For example, g is a polynomial function. We say that this parameterized algorithm admits a polynomial kernel. Okay, if it's an exponential, then we say that it admits an exponential kernel. Right. Okay. So this clear? So definition clear? We are going to continue pre-processing the input till its size is reduced. Okay. Right. Let's start with again vertex cover. Okay. So for any problem, it's enough to have some kernel, right? Even if it is exponential kernel, we'll get an exponential running time or an FPT running time. But there is also the people who try to optimize the size of the kernel, like find if there is an like if you know given an exponential kernel, can you reduce it to a polynomial kernel? Like for example, can you reduce it to a kernel of size k cube? Then if you have k cube, can you optimize it into k square and k and so on? So these are like relevant problems. Also similar to interactability in FPT algorithms, there is kind of lower bounds for kernelization also. There are some problems for which you can prove that kernels better than something cannot exist. Like there are some problems for which kernels better than k square cannot exist or k cube cannot exist. Or there are some problems where a polynomial kernel cannot exist. And so, okay, we are not covering all this. Okay. So just vertex cover. Okay, so these are the reduction rules. Okay, first one is if G contains an isolated vertex, delete V from G. What do you mean by an isolated vertex? Vertex with no edges, right? Then delete. This is trivial. Why this is okay. Next is this. If there exists a vertex of degree at least k plus 1, what can you say about such a vertex? So you have a vertex and its degree is k. So what is our problem? We are trying to find a vertex cover of size k. Okay. So we have a vertex V with k plus 1, degree k plus 1. What can you say about that vertex? Okay. What is your first statement?
The neighbors of this vertex will be part of a vertex cover as
But there are k plus 1 neighbors. It has to contain V, right? So what happens if V is not in the vertex cover? Yeah, then we have to pick all its neighbors. There are at least k plus 1 neighbors which exceeds our budget of k. So if there exists a vertex cover of size k, then V has to be in it. Okay. So that's what we are saying. That's this reduction rule. If there is a vertex V of degree at least k plus 1, then delete V. By delete V, I mean I am adding it to the vertex cover and decrement the parameter k by 1. Reduce the budget by 1 because I have already added k to it, V to it. Right? Okay. So that's my reduction rule. Simple. I just have these two reduction rules. Okay. So I do it for as long as I can do it. What can you say about the reduced instance after I run all these reduction rules? These two reduction rules. There are no isolated vertices. Every vertex has of degree at least 1. And what is the maximum degree of each vertex? K plus 1. K. At least K. Okay? Right. Now, assume this reduced graph has a vertex cover of size K. Right? So, now every vertex in the vertex cover, how many edges can it cover? What is the maximum degree? K, right? So for every vertex there has at most K edges. So every vertex can cover at most K edges. Right? Okay. So if there is a vertex cover of size K, it will cover all the edges, right? So a vertex cover will cover all the edges, and let's assume that there exists a vertex cover of size K, and the third statement is every vertex can cover at most K edges. What can you say about the number of edges in that graph? See, we have, let's say we have a K-sized vertex cover. It covers all the edges. Okay. Cover all the edges, and each one of them can cover how many edges? K edges, right? Each of them can cover K edges. There are K many vertices in the vertex cover, and all the edges are covered by some vertex in the vertex cover. How many edges are there? K square, right? Every vertex can cover K edges, at most K edges, and all the edges are covered. That means there are at most K square edges, right? So we got a graph with K square edges, right? So the reduced instance has only K square edges. What about, can we bound the, yes, I want to, see, we are assuming, so assume that it has a K-sized vertex cover. Okay, it has a K vertex cover. By the reduction rule, the maximum degree of each vertex is K, right? So that means any vertex in the vertex cover can cover at most k edges, right? Okay, and all the edges are covered by one of the k vertices in the vertex cover. And how many edges can be there at most? Every vertex in the vertex cover can cover k edges. There are k vertices in the vertex cover, so it's k times k square. Okay, so there is at most k square edges, vertices. So we have bound the number of edges by a function of k. Can we bound the number of vertices also? Yeah, how?
That will be when you have k independent stars.
Yes, in the worst case, like you have one vertex and has k neighbors, so all of this will be k plus, a group of k plus 1 vertices. Similar, at most there can be k such group, so it is k multiplied by k plus 1. So I repeat, so here again k, every vertex have k neighbors, right? So each vertex in the vertex cover plus its neighbors gives you k plus 1 vertices. Okay, there are k such vertex covers. In the worst case, all of them may be disjoint. Okay, then also you can have only k into k plus 1 vertices, which is k square plus k vertices. Okay. So after this, we have this. The graph has maximum degree d, then a set of k vertices can cover at most k d edges, and gk is a S instance, then gk is a reduced instance, then v is then the number of vertices is k square plus k, number of edges is k square. What happens if the edges is more than k square? You can directly say no, right? So you have proved that if there is a vertex cover size k, then this is the size. If after reduction you get an instance which is greater than this, you directly say no. Okay, and if the size is this much, do you know that? Can you say that it's a yes instance? Does it mean that it's a yes instance? No, right? Need not be. But now the instance is, the size of the instance is bounded by k. You can by brute force find all the vertex covers and check each of them, or you can use some clever other method. But anyway, you can do it in FPT. The running time will be in FPT. Okay? Questions? Okay. So vertex cover parameterized by the output size as a kernel of k square vertices and k square edges. We have one more thing. You see, 10 more minutes. So. Okay. So next problem is edge-clique cover. Right. So edge-clique cover problem is this. Given a graph, decide whether all the edges can be covered by some clique. So clique is a complete graph. Okay, so you are given a graph. So you are given a graph. You want all the edges to be covered by some clique. Okay, so how can you do this in this graph? So this is one clique. So triangle is a clique. You have covered these three edges. Again, to cover this, you need two cliques, right? So again, this triangle is a clique. This triangle is a clique. You want to cover this edge also. So you take this K2. Just this edge. Okay. So the question is, what is the minimum number of edges you need? Okay. minimum number of cliques you need. Or in the decision version is this: given a graph G, decide whether the edges can be covered using at most k cliques. Okay, is the question clear? Can we cover every edge using at most k cliques? Okay, and right. So the reduction is this: remove isolated vertices. It's fine, right? Isolated vertices anyway, it's not going to be. There are no edges in it. So next, if there is an isolated edge, by isolated edge I mean two vertices of degree 1, which are joined by an edge. Okay. If you have such an edge, what can you say? There is only one way to cover that edge, right? Take that edge. So then that's what you're doing. You're deleting that edge and decrease the budget by 1. It's isolated vertices. The next reduction rule is this: if there is an edge UV whose endpoints have exactly the same closed neighborhoods. So there is an edge UV and the set of neighbors of U and set of neighbors of V are the same. That's what I mean by they have the same closed neighborhood. U and V has an edge between them, and also other neighbors of U and other neighbors of V are the same. In that case, you delete one of them. Okay. So why is this fine? So I'm not doing anything to the budget. I'm just keeping the budget as it is. Number of won't change. Yes, you have to say that. The number of cliques in the instance, and even after deleting V, it's the same. Yes. Yes. Any clique that contains U, yes, V can be contained, and vice versa, right? So in the reduced instance, you get a clique. So since they have the same neighborhood, any clique U is contained in, V also can be added to it, and it still remains a clique. Okay. So maybe I'll just stop with this, and you think about these reduction rules and see what is the kernel you will get after all this, applying all these reductions. We'll discuss in the next class. So these are the reduction rules. See what kind of kernel you get after this. Maybe I'll give you a hint. The kernel size is 2 power k. Just prove it. Where FPT is algorithms? Where this FES prob or edge? Okay, are you asking about the problem edge clique cover in particular or kernels? Okay, so I don't have any concrete applications to tell you because all of these are abstract problems, but see, there are 2 or 3 areas that I talked about. All these graphs, yes? Graph? Yes, that's what kernelization is doing, right? So all these graph problems are relevant because you see graphs everywhere, right? Everything around, I won't say everything, a lot of things around you can be represented as a graph, right? Like the road, be it the road network or be it your social network.
particular algorithm is there. I can get one instance of this.
Okay. I'll give you an example, or maybe can we take it offline and right. No. It should be an if and only if, right? If n of u is a subset of n of v and you delete u, I don't think it is. It's only one direction, right? Other direction. Okay, so there are some problems. You can take this, try solving it. We'll hopefully discuss it in the last lecture. So this is on bounded search tree and kernelization. And next class we'll think about this problem, and we'll start with a new topic in the next.